And so before really going into the definition of what say Kripke-Platek set theory is, let me say start with some motivational part of actually from that led to development of Kripke-Platek set theory. Okay. Okay, so consider a standard model of first-order arithmetic. So as usual, so we have natural numbers, comparison, constant 0 and 1, addition and multiplication. Okay, so as usual, delta 0 formulas are formulas such that all quantifiers in them are bounded. So as usual, bounded quantifiers are quantifiers of this form. So for x less than t psi of x. Okay, so it's, as usual, this is just this kind of operation. And so and exists x less than t psi of x. And as usual, so this is this kind of operation. So yeah, it's more standard. Here's a type. Of course, it should not. This should not be psi, but rather it should be t. So of course we don't want to have bounds, bounding terms that also depend on the variable. The bounds. Then it would be really meaningful bounding. Okay. Yeah. So some examples of delta 0 formulas. Okay, so yeah, so basically you could use bounded quantifiers, yeah, it's standard stuff, and so but if you have some unbounded quantifiers, this wouldn't be a delta 0 formulas, and if you have, as I said, if you have this bounded quantifier, but when the bound is depending on the variable that it bounds, it's also not about delta 0 formula, so this is not a valid form of bounded quantification. Okay, and of course, plus sigma 1 consists of all formulas of the form exists something and then delta 0. Okay, so now of course there is this connection between computability and sigma 1 definability. Okay, as usual, so we say that the set of naturals of a set of k tuple of naturals definable by formula with k free variables if it's defined in the standard model of arithmetic. As well, we could talk about definable functions as well as definable partial functions. And basically, the definability of a function or definable partial function simply means that the given formula defines the set that is the graph of this function or graph of the partial function. So basically, this is how this standard definition works. Okay. So this is basically below are some standard facts. It's a bit, I think with the history of this fact, I'm actually not precisely sure about history of this fact. To some extent, they could be attributed to Gödel, but in fact, so basically, so in the time of when Gödel worked on this, so it's basically I think this was introduced in his lectures that he gave after he developed incompleteness theorems. There was, in fact, back then there were still no Church-Turing thesis. So basically, it's not. It's perhaps it's not completely fair to attribute this together because back then they really know this notion of computability as this, in the modern sense. It really depends on Church-Turing thesis. However, basically, Gödel already had this notion of general recursive function that turned out to be the same as computable function, and so he proves this kind of fact for this so general recursive functions. Okay, nonetheless. So now let's go to this standard function. Basically, standard function is that a set is sigma 1 if and only if it's computably enumerable. A function, so a set would be computable, or what, or else people say decidable, if and only if it is sigma 1 definable and its complement is sigma 1 definable. Else, so this it's called delta 1 definability. So it just means that the set and its complement are sigma 1 definable. And finally, so the functions, so computable functions are against exactly sigma 1 definable functions, and partially computable functions are again sigma 1 definable partial functions. Okay. So basically, you have this now in case of arithmetic, you have this very nice connection between sigma 1 definability and computability. So basically, this means that sigma 1 definability is in a sort of essentially could be regarded as a model of computation. Okay, so and to remind you how this is proved, of course, so basically it's done basically when you because in arithmetic you could develop this coding of sequences, and basically using the coding of sequences, then it's easy to say embed Turing machines or your other preferable model of computation inside arithmetic. Okay, so basically standard stuff. Okay, so but of course, so but basically the same would work on other structures as well. So other natural structure where we could consider computability is the structure of all hereditarily finite sets. So let me remind you, so basically hereditarily finite sets are sets such that they themselves are finite and all the elements are finite, all the elements of the elements are finite, and so on. Or it could be it could be defined by this induction. So basically, so empty set is so hereditary finite, then all the power set of empty set is a set of hereditary finite sets, and so on. So basically, so basically, HF is the same as omega's level of cumulative hierarchy. Okay, so of course, so we could identify HF with this corresponding set theoretic structure. So basically, HF together with the membership predicate. Okay, so as usual, so we also have bounded quantification in set theoretic language. Yeah. Yeah. So yeah. So we have this bounded quantification set theoretic language, and again, so in fact we have exactly the same correspondence. Okay, so this, so basically hereby say are computably enumerable set or computable set of hereditary finite. That means the form. So basically, you could encode. So if you consider some standard model of computation, you could encode hereditary finite sets by natural numbers or in some other way via coding, and hence you could talk about this. Some set of hereditary finite sets to be, for example, computably enumerable. And the same way you could talk about computable functions. Oh, okay, and in a sense, HF is a rather natural model of computation. So basically, this object. So because in sense it's even more natural model of setting for computations than natural numbers, because unlike natural numbers where you actually need to do some work to do coding of sequences. So I remember this. But here it's more or less straightforward. So basically, it's possible to encode ordered pairs in a say standard set theoretic manner by Kuratowski pairing. So which of course is very straightforward encoding, and then it's just when you have this pairing function and you have sets. Basically, it's in a very straightforward manner. You could encode all the kinds of finite objects, and in this sense, so it's even much easier to talk about computability in HF than in naturals. Okay, but basically, so it is the same thing. Okay, so now let's go to some generalization of computability theory by the same approach. Consider rather than considering HF, let us consider HF of M. So where M is some first order model. So what's going on here? Okay, so now what we want to do is to define the computability over a structure. So basic premise is something like this. So consider, for example, a set of reals. And now what we want to have is that we want to have some kind of fine computations, but the computations that would manipulate with reals. And for example, we would like this computation to have access to arithmetical reals, so addition, multiplication, subtraction, so on. Yeah, but so we, for example, we don't want to have, I don't know, some more powerful access to reals. For example, to treat reals as just some oracles and something like this. So yeah, so we want to do something like this. So basically, we want to have this model of computation that is allowed to manipulate these reals and but only use arithmetic conversions. So for this, basically, we could simulate, basically define this model of computation in terms of relativized hereditary finite universe. So now what basically we consider the sets now rather than considering just this sets built out from empty sets, so in this Zermelo-Frankel fashion, rather than that we'll consider sets with your elements. So your element is, so basically it's a bit different setting of set theory. So when we have two distinct kind of objects, so we have sets and we have your elements. And the idea is that your elements, they could be elements of sets, but they are not sets themselves. So all your elements in this sense are empty sets, but so basically, your elements don't have any elements themselves, but they could be elements of other sets. Okay, so then we just basically relativize construction of hereditary finite sets to the domain of some model M, where we treat the elements of this domain as your elements. So basically, and then we basically allow this finite sets built up from elements of M. Okay. And yeah, and then in the same way we define this notion of sigma 1 formula in HF of M. So now when sigma 1 formulas we allow to use this additional predicate symbol that were present in model M. And this actually gives us this rather natural notion of computability of a given model. Okay, okay, so this is a second mathematical example. Okay, yeah, okay, so this is just definition of constructible sets for people that are not familiar. Okay, to remind people what constructible sets are. So basically, as usual, so constructible sets are defined by recursion on ordinals. So yeah, so we start with empty sets, and then we iterate first definability with parameters over each previous level. So basically L alpha plus 1 is a set of all subsets of L alpha that are definable, first order definable in L alpha. And in limit stages we take unions. Yeah, and of course HF is just L omega. Okay. So now, yeah. Okay. And so now, actually, it's in certain sense, it's natural to consider this restricted. So if you, so basically now what we want to have is some kind of notion of computation that uses or so that is connected to ordinals. There are several ways how one could make this work, and I will talk about so basically here I will talk about one of these approaches, which so there are some indications in the so there are a lot of reality of what is going on. But okay, but first before this, let's just discuss of how in principle this could work. So okay, so we have this now. We have the structures L alpha, and of course we could regard them as models in set theoretic language. So L alpha, and so where we have L alpha, and we have the membership predicate. And now the idea would be to equate computability with sigma 1 definability as we have done before. However, in fact, so if you can consider just some arbitrary alpha, you might not get something particularly nice if you do something like this. So, okay, first of all, basically, if your ordinal is not limit ordinal, it's complete mess. So of course, even for example, you don't so given two sets. It's not always the case that Cartesian product of the sets will be in L alpha. So if alpha is not the limit, so it would be really bad. Furthermore, for arithmetical, so again, if alpha is small enough, so if alpha is not close enough ordinals, that arithmetical ordinals would be a mess. So for example, you need ordinals for omega to beta, even for addition of ordinals to be total, for example. And for example, if you want exponentiation on ordinals to be total, you need your ordinal to be epsilon number. But okay, it's kind of a small thing. So I think the larger restriction is something like this. So if so suppose we have some set, and we have some compute so sigma 1 definable function. So we want the idea would be that sigma 1 definable functions should be analogs of computable functions. Okay, so we have some set. And so we want the sigma definable function to be defined on the whole of the set A. Then, so it would be very natural to assume that the image of this definable function should be a set. So basically, if you apply a definable function, a sigma definable function to a set, then its full image should be also a set. So I think it's very, so it seems to be a very reasonable assumption. However, it doesn't really work for small enough alphas. For example, it doesn't work for omega plus 1 with the following example. Consider this iterated Turing jump function, so that maps inertial number to nth Turing jump of 0. Yeah. Okay. And in fact, so it will be sigma 1 definable function in L omega plus 1. However, the set of all Turing jumps wouldn't be element of L omega plus 1. So it's okay. Is it correct? Yeah, right. Yes. So right. This should be correct. Because in fact all the point is that all sets in L omega plus 1, so all subsets of natural in L omega plus 1 should have are arithmetical. So because they're definable over L omega, and so L omega was just HF. So basically, the sets that are definable in L omega are more or less arithmetical sets. And because of this, all individual Turing jumps are actually elements of L omega plus 1. But the collection of all Turing jumps, or all finite Turing jumps, wouldn't be in L omega plus 1. Okay, but basically, so so by slight modification of this example, we could show that that this that we wouldn't have an image of say of natural numbers under this under certain function or under certain sigma definable function, or in all L alphas where alpha is a computable ordinal. So I recall that computable ordinal is an ordinal that is the order type of some computable ordering. Yeah. Yeah, so basically the idea, this example would be more or less the same, but rather than taking this n iterate of Turing jumps, we need to take some transfinite Turing jumps for basically so this, of course, L alphas for this computable alpha, they basically have this hyperarithmetic degrees, and so basically then you just need to choose the right amount of transfinitely iterated Turing jumps to basically have this property that you have all the Turing jumps up to a certain level, and some points break apart. So, but you don't have the collection of all the Turing jumps. Yeah. However, so but basically this stops. So, but basically, as soon as we get to the level of omega 1 Church Kleene, where omega 1 Church Kleene is a supremum of all other types of computable ordering. So it's first non-computable ordinal. Then actually it's we get some decent properties. For example, of course, we have totality of all the ordinal arithmetic, the smallest straightforward. And so what is more important, we actually get this property that if you have sigma 1 definable function and that defined on a certain set, then the full image of this function, of the set under this function, will be an element of your L omega 1 Church Kleene. Yeah. Okay. So, okay, it's actually not exactly trivial fact that it's true, but however, it's true. So, okay. So, well, okay. So now this was the motivating part. So now let's go to Kripke-Platek set theory. So basically, what we want to achieve with Kripke-Platek set theory is that we want to have this notion of the set theoretic model where we could have where sigma 1 definability works like a decent notion of computation. So this is basically the motivation of this. Okay, and so here are the axioms of Kripke-Platek set theory. Okay, so of course we have axiom of extensionality, axiom of pair. So axiom of pair says that so for any set x and y, there exists set z such that both n, x, and y are elements of z. Okay, then we have the axiom of union. Basically, again, just say that given a set x, there exists. Okay, basically from it follows that given a set x, there exists a set that is union of x. So what is important? We have axiom of delta zero separation. So of course, so this is of course different from Fermat-Fraenkel set theory, where you have unrestricted scheme of separation. However, here separation is restricted just to delta zero formulas. So it's very natural because so of course delta or any delta zero predicate in fact will be computable under our notion of our idea of what our notion of computation should be. So because of course any if you have some delta zero property, then it's simultaneously sigma 1 and its negation is sigma 1. That's basically everything is delta zero definable should be like this generalizedly computable, and of course we want to have separation for this computable properties. So we have delta zero separation. And then, so basically, I think the next section probably is the most important one. So this is the principle of sigma 1 collection. So basically, collection is something very similar to replacement, but it's not. But basically, in the case of cerebral Frankenstein theory, so usually it's axiomatized using replacement, but then actually you could prove collection from replacement because cerebral Frankenstein theory is very powerful one. Okay, but so. And also, what is replacement? So replacement says the following. So, if basically, if you for all elements in a given set, you have witnesses for some property phi, then you have then you could restrict your witnesses. So basically, you have this all-encompassing set such that you could always find your witnesses in this set. So it's similar. It's similar to replacement, but in the case of replacement, so in your premise you would say that you have unique witness Z, and then you could just collect these unique witnesses. But actually, but actually, it will be more restrictive axiom because in order to apply replacement, so you would need more not just guarantee that something exists. But there exists unique object with this given property, so collection is say more easy to apply. Okay, and basically, so if we go back to this to this our discussion of computation, so basically this collection is corresponding to this property about. So because of here we have this basically. So when we discuss this application of computer function, essentially we discuss this certain instances of replacement, and so actually collection do imply replacement, but in a certain sense it's better to consider collection rather than replacement. So basically what we're talking about is this slightly generalized. Slight generalization of this replacement for restricted to computable functions. But yeah, so this is basically what sigma collection is. And finally, so Kripke-Platek theory contains a scheme of foundation. Basically, I think so. This is kind of less important component of Kripke-Platek theory, but basically the point is that if you consider transitive models, and so in a lot of applications of Kripke-Platek theory, of course, basically what you want are transitive models when you have real, so basically when you have the real membership predicate, then of course you get a foundation for free. Because any transitive model will be both founded from external point of view, and what foundation said is that basically you have from founders for definable subsets of a model. Oh, sorry, here's a typo. So foundation. So I put this negation symbol here, but it should be over phi here rather than outside. Yeah. So, but make it just say that. So if you have some definable property phi that there exists at least one element, then there exists a membership minimal element that satisfies this property. So this is what's going on here. Okay. So this is Kripke-Platek theory. Okay. Else, actually, it will be useful to consider the case of series with your elements. Basically, we already discussed this case when we discussed this structure HF of M. But okay, but now let's do it in a more general fashion. Okay. So basically, this is kind of this to do it as in a natural way. So we will have this a bit unusual language. So when we have three sorts of variables, so we have variables for that range over arbitrary objects. So x, y, z, w. It's I don't know something x1 and x2 and so on. So basically, this kind of symbols. Then we have variables that range over sets, and we have variables that range over your elements. And so then we assume that actually our signature contains some, in addition to membership predicates, have some predicates that are applicable just to your elements. Okay, so here we have some presumptions about the models. So the presumptions are the following: so that so basically the domain of the model is split into two parts. The part of the domain that is objects that are sets, and there is the part of the domain that consists of objects that are your elements. And so then we have the initial restrictions on membership predicate and predicate Ri. So basically, your element shouldn't have any shouldn't have any members. So nothing could be a member of your element. And and basically, so predicates Ri are defined only on your element. So if you put as one argument something that is a set, then automatically Ri should be false. Okay, so again, we have notion of delta 0 formulas and sigma 1 formulas. So of course, so here in a sense we have like six kind of meaningful bounded quantifiers. So basically, so when we bound something by a set, we bound something by arbitrary object, and then there's three variants of what you bound for either set, arbitrary object, or your element variable. So but it's just syntactical stuff. And so of course, if you don't like this say unusual variant of first order language, basically this could be regarded just some syntactical sugar or over the usual one sort of first order logic like this. So basically you add to your first order logic additional predicate u. So it will be unary predicate with intended meaning that so your of x holds if x is a your element. And then basically these conditions 1, 2, 3 could be stated as just additional. So basically you have this. So basically one is kind of automatic because basically of course predicate, so it's a unary predicate basically always would split your domain into two disjoint parts. And then, so of course, so then you should have elements, axioms that say that your elements do not have elements, and there should be this axiom that say that states this restriction free. And then, so this sorts of free source of variables that we have could be simulated in a straightforward manner. So basically, if you have so this quantifier over arbitrary objects to be translated just as quantifier, just usual quantifiers, then quantifiers over sets would be interpreted as quantifiers for x if x is is not an your element, then, and so quantifiers over your elements would be interpreted like something like this. So, for example, if there exists your elements, like there exists objects such that if object is in your element, then and so on. Okay, so there exists, so not then but and. So so basically it's done very straightforward. Okay. No, but basically, of course, it would be much more convenient to use this variant of the language. So then we have the theory KPU. Okay, so basically theory KPU is the same as the theory KP, but that allows your elements. So it's more or less the same thing. So basically what's going on is that so extensionality is we have this version of extensionality that work only for sets. So basically, if two your elements have the same member, so it's entered. So it's the case, they're not necessarily equal. But basically, other than that, so it's more or less the same theory. Okay. Yeah, and so yeah.
So this KPU is that there is an axiom about U, right? It's missing in the slide.
Yeah, you state for your elements. So basically, this is basically KPU means that version of KP where we allow your elements.
Yeah. Anyway, for people familiar with this, yes, it's okay. But for the beginner, maybe. Anyway, here for different variable, you have different scope. For these, for our object, for AB is only
yes.
for
Yeah. But basically, I think basically it's very intuitive. So basically, but the point, so of course there's this convention, but I think in practice it should be very intuitive, because basically in most cases, so when so it's very clear what we want to quantify. I mean, so it's basically if you look, so you consider the meaning of subformula, basically, so it's more or less clear whether you want to quantify over arbitrary objects, or you want to quantify over sets, or if you want to quantify over your elements. So typically, actually, you almost wouldn't have quantification over your elements, just quantification over sets and arbitrary objects. Yeah, so basically there is this convention, but I think so in fact, so in practice, in most cases, very even if you don't remember what was this names of variable, so what was those alphabets, it still will be very easy to figure out what is going on. Okay.
Okay. Thank you.
But okay, but basically, so it's I think it's basically the same theory. So if you consider this and this, so you have. So we have the same actions. Basically, the only thing that I have done there is that I renamed some variables that before were over arbitrary, were just x's or y's, to this variables that range only over sets. So because sometimes, because for example, extensionality works only for sets. So when you talk about separation, of course, you want to make separation from a set, etc. But it's basically those restrictions are extremely natural ones. So it's yes. So it's nothing really interesting going on here. Okay. So now let's finally prove something. I will prove that much today. But okay, let me. So demonstrate you how it really work inside Kripke-Platek set theory. So because of course it might in first glance look rather restrictive. So for people familiar with CFC but not with KP. Okay, so here is basically the standard example from where more or less all the people start the presentation of Kripke-Platek set theory. So the theorem that Cartesian product exists. So as usual, so we define pairing by Kuratowski pairing. And Cartesian product, of course, is just a set of all pairs. One component is an element of function, and the other component is an element of the other set. And so this is actually happen to be provable in KPU. But we need, I guess, to work a bit more. Comparing to the case of ZF, it's done as follows. We consider some sets A and B want to construct this Cartesian product. Notice that the property that is equal to the pair xy in fact is expressible by delta zero formula. So here I've written this formula down. So here is this formula defining the property. Okay, so basically it said something like this. So that there exist two. set that it is two elements in the set Z. Basically, the idea, of course, would be that Z1 corresponds to this singleton X, and Z2 corresponds to a set consisting of X and Y. So basically, we write down that basically the following, so that Z1 is actually is a singleton X. So it's, of course, and so here it's done in this delta zero fashion. So here it is. So of course X should be element of Z1, and so all elements of Z1 should be X. Then so we have this definition for Z2, so that it's actually the set consisting of X and Y. So here are those properties. And finally we say that all elements of Z are either Z1 or Z2. So, and of course this G has this, and you see this delta zero formula, and of course this delta zero formula defines the properties that Z is equal to pair XY. And so, and to mention, of course, with using axiom of pair, it's quite easy to prove in the KPU that for objects XY there exists ordered pair XY. So basically, you apply this axiom of pairing several times, and you obtain this set. So it's very straightforward. Yeah, so more or less the same what people are doing in the case of the basic development in CF. But okay, so then the point is, as soon as we have this delta zero, we see that Z equal to XY delta zero property, we could apply collection. So namely, we have yeah. So of course, for X and Y, we have this pair. Thus, basically now applying collection to the set B, we see that we fix some X in A, and then we see that by collection for Y and B. So we fix some X from A, and we see that there exists this set C that contains all the pairs where first component is this fixed X, and the second component is arbitrary Y from the set B. Yeah, so basically this section of Cartesian product. Yeah, model some separation, but basically, so the C could contain some additional element, but then we could remove all these additional elements by delta zero separation. So thus we obtain this. We see that we have this sections of our Cartesian products for all fixed X. Then actually it's quite easy to show that property to be the section of Cartesian product. So the set. So this property C is equal to this set. So basically, this is a property with two arguments, C and X. So it's also delta zero. And then we apply collection to this property. So because now we know that for all X there exists this section of Cartesian product, and thus we have this encompassing set that contain every single section of Cartesian product. Then we could remove all the elements in the set that are not the sections of our desired Cartesian product. And finally, we have the set that D that so consists of all the sections of our desired Cartesian product. And finally, we apply axiom of union to this set D, and we apply our Cartesian product. Okay, so it's very straightforward. Okay, so let's prove something a bit more advanced. Then in fact, basically so there is a class of formulas that is kind of similar to the class of sigma 1, but in certain sense is less restrictive. So namely the class of sigma formulas. Yeah. So basically, sigma formulas are formulas such that we allow arbitrary propositional convectives allow arbitrary bounded quantifiers. However, unbounded quantifiers are such that so in positive positions we are allowed only to use existential quantifiers, and on negative positions we are allowed to use only universal quantifiers. Yeah. So in a sense, this is generalization of plus sigma 1. So basically what the only thing that we done is that we allow to kind of this mixture of existential, unbounded existential quantifiers and bounded quantifiers. So in class sigma 1, so we had this leading existential quantifier, and only then we could have bounded quantifiers. But now we could have something, the situation when we first have, say, something like leading bounded universal quantifiers, and only after that we have existential quantifier, and so on. So basically, this is kind of this less descriptive version of class sigma 1, but this kind of captures the same thing. So if we've done the same in arithmetic, so we would have, of course, this sigma 1 definable sets would be the same as sigma 1 definable sets. Yeah. Yeah. So, and in fact, this also work. So one of the reasons why KP is this natural setting for generalized computability is that so actually the same connection works in Kripke-Platek set theory. So basically, Kripke-Platek set theory proves that so basically over Kripke-Platek set theory, it's possible to transform equivalently transform sigma formulas into sigma 1 formulas. Okay, so how it's proved? Okay, it's rather easy. So first of all, let's deal with the negation and implication. So basically, we eliminate all the negation and implication from the formula by pushing the negation downward to the level of atomic form. So basically, first we transform. So we express implication in terms of disjunction and negation, and after that we use De Morgan. So basically, the Morgan laws to push negations on the level to the level of atomic formulas. And after that, we have this formula where we have conjunctions, disjunctions, bounded quantifiers of both types, and only existential unbounded quantifiers. And for these formulas, we prove the theorem by induction construction of the formula. Now, so basically, so what we need to show is basically that so conjunction of two sigma 1 formulas is sigma 1, disjunction of two sigma 1 formulas is sigma 1, bounded existential quantifiers over sigma 1 formula is sigma 1, and bounded universal quantifier over sigma 1 formula is equivalent to sigma 1. Actually, all these cases are trivial, other than this bounded universal quantifier, because of course it's for conjunction, disjunction, and about existential quantifiers, it's easy to put them inside the formula. There are no issues there. And for bounded universal quantifiers, we simply use collection. Yeah, so basically, so if we have the formula for x from A, there exists u such that psi prime, then actually it's going to for formula exists B such that for all x in A exists u in B such that psi prime. And basically, this is easy to show by using axiom of collection. So the point is, so basically, this is here we have this bound A, and then for the set A, we have this bunch of witnesses for various elements of A. And then as B, we take our encompassing set. And this is how we show that. So this formula implies this formula. And on the other direction, it's very straightforward. So basically, it's very easy to see that this formula implies this one, because basically here we have bounded existential rectifier, and here we have unbounded existential rectifier. And of course, if we have bounded witnesses in some bounded domain, then we will have witnesses in unbounded domain. Okay, so this is okay. So this is basically how it's done. So now we transform formulas by induction. And so basically by induction we put this equivalent transformation of sigma formulas into sigma 1 form. Then the standard fact is sigma reflection. Okay. Yeah, so basically there is this very natural principle in Kripke-Platek theory. Yeah, so okay, if you first recall that relativization of the formula is a function. Basically, if you take some formula phi, then relativization of the formula phi to a set A is a formula where we replace unbounded quantifiers, all unbounded quantifiers with bounded quantifiers, where bound is our set A. So basically, idea is that so if you think about A as a transitive model, then basically this would mean that you simply so look at truth value of this formula inside a transitive model. Okay, so actually there's at least as long as this if the parameters of the formula are inside A. So if not, that it's a slightly different thing. But okay, well, basically in the case of A is a transitive model and all the parameters of the formula phi are elements of A, that phi A is just to the relativization of formula phi to the transitive module A. Okay, and then so we have this sigma reflection principle. So essentially, you could think about it as a statement that says that if some sigma formula holds, then there exists a transitive module of the sigma formula. Yeah. Yeah, in fact, it's very easy to prove using sigma sigma collection. Yeah. So basically, so for people that are familiar with the reflection principle in usual thermodynamic Franklin theory, basically it's a very simple proof. I think probably it's even easier one because we don't even need to deal with universal unbounded universal quantifiers and so nested quantification. Okay, yeah. So basically, the proof. So the point is that we prove the reflection by induction. Yeah, and so the key properties that we're using is that actually the sigma formulas are upward persistent. So if A is a subset of B, then phi of A implies phi restricted to A implies phi restricted to B. So if sigma formula holds on smaller domains, then it holds on larger domain. And of course, if sigma formula holds on some restricted domains, then it holds on unrestricted domain. And then basically this allows us for very easy proof by induction. So basically we then kind of basically due to this persistent, so when we say have this Boolean connective, so we could join the witnesses. So and when we have bounded quantification, we could take this, the common bound for all the bounds. And we could do it by collectors. Yeah. And this allows to prove sigma reflection. And in fact, so the nice feature of sigma reflection that it's allowed for a more compact axiomatization of Kripke-Platek's theorem. So in fact, it's possible to remove from axiom of Kripke-Platek's theory axioms of P, union, and sigma one collection, and just to have axiom of sigma reflection. And this will give you the same theory. So the trick is that basically by using sigma reflection, it's possible to prove both axiom of P and axiom of union, and of course axiom of collection. But it's I think, yeah. So basically, it's like okay. So it's more fairly easy, but so people who are interested could say do it as an exercise. Okay. Okay. So. Oh, okay. So finishing up with this. Develop some basic, showing that so KPU is capable of some basic set theory. Let's develop this recursion on ordinals and sets. So, okay, so let's show that. So let's start with ordinal arithmetic. So, of course, first recall that set is called transitive. It's if all its members are its subsets. And so in the case of sets of zero elements, so basically the point is that so transitive sets are allowed to have members that are Euro elements, but all the members are that are sets should be the same type subsets of a transitive set. But how ordinals are not allowed to have members that are Euro elements, and as usual, ordinal is a transitive set such that all its elements also are transitive sets. Okay, and as usual, we have successor operation on ordinals. So we have here you could see the standard definition of arithmetic on ordinals. And so now the point is that to carry this definition out in Kripke-Platek's theory, what we want is to use recursion on sets. And in fact, in Kripke-Platek's theory, we could do a recursion for sigma 1 definable function, or basically, or just what it means is computable functions. So, but computable, of course, here we don't need computable instances, but in this relativizeness. So, yeah. So basically, this is a direct analog of primitive recursion. Basically, it's primitive recursion on sets. So, given some function f with some maybe bunch of side parameter x, so argument y and argument a, we define a function g. So now without parameter a by this. That is basically by recursion. So basically we take so the value on given y is f applied to this partial to the graph of g restricted to the set y. So basically the point is that so we want to have this definitions of function by transfinite recursion on sets. So we want to define value each next value of our function using value for our function on elements of the set on which we're defining our function. And then so this function f is a function corresponding to the step of recursion. So it takes one parameter so set on which we're defining function g, and other parameters so the values of g on all the members of the set y. Yeah, and of course, so yeah, so this is yeah, and so this in KPU it's possible to show that this way we could define computable functions. And so okay, so what is the idea of the proof of this fact? So basically, it's rather straightforward. So yeah, so basically what we want to have the we build the sigma definition for function g as well. So we say that so value of g on given xy is something if there exists this partial graph of g on the transitive closure of set y such that it's abide with this recursive definition. And basically this will be the definition of sigma definition of function g. And then we show that so this definition indeed works, so that it's indeed defined this total function as well. So basically we make the proof by foundation, and for the each step we need to use axiom of collection. So basically the axiom of collection is necessary to obtain this kind of sets. So here is the place where axiom of collection goes into play here. Okay. Yeah, and in fact, so it was possible to prove this fact using just sigma-1 foundation. So we really don't need the full scheme of foundation to establish such basic facts. In a sense, it's similar to the situation in piano arithmetic, where you don't really need the full scheme of induction to prove that all primitive recursion functions are total. So you really just need sigma-1 induction, and here you need just happen to need just sigma-1 foundation. Okay. Actually, I think in the terms that I formulated, it's like more like pi1 foundation, because foundation is more akin to least element principle, as I've formulated it. But okay, yeah, so it's pi1 foundation. But basically, there's other way to. So basically, if you reformulate foundation in terms of induction on sets, then it would be sigma-1 foundation. Okay. So yeah. So this is basically this is primitive recursion function set. So yeah, so it's actually quite natural class of functions, and you basically could define a whole bunch of say this basic operations on sets in terms of primitive recursion. Okay, so now let's go to discussion of transitive models of KP. So as usual, so transitive models are simply transitive sets that are considered to be models in the signature with membership predicate. So HF is of course the least transitive model of KP. So now it's very boring. Okay, so the first interesting thing happens if we go beyond HF. So this is KP, necessary KP omega. So that is the extension of KP by the axiom of infinity. And of course, by infinity here it means the axiom that essentially says that ordinal omega exists, or something equivalent. Because of course, I'm not sure actually. So if you what exactly was happening if you formulate axiom infinity in some weird way, so I think actually you probably there should be some regardless. So and of course the least transitive model of KP omega is L omega 1 Church cleaning. And so in fact, so this is also it's not I would say it's not very difficult proof, but I need to do some work to show that L omega 1 Church cleaning actually is a model of KP omega. And of course the hard part is to show that it satisfies axiom of collection, because of course all the other axioms are satisfied on all L lambda, where lambda is limited ordinal. However, of course, collection is not that easy. And so here we somehow need to collect axiom of collection with the notion of first non-recursive ordinal. And basically to do this, okay, so basically for people that are familiar with the recursion theory of pi11 sets, it's the proof for something as follows. So basically, assuming that the idea would be like this. So suppose we have a failure of collection and L omega 1 charge linear. What would it mean? It would mean that we have this essentially so we have some delta zero property such that so it's so delta zero in L omega 1 charge linear such that it's witnessed by so basically we have some set in L omega 1 charge linear. And then we have this sigma 1 function such that it ranges is cofinal in ordinals, so something like this. And basically then from this it would be possible to cook up sigma 1 sigma 1 predicate definition for the property of recursive recursive ordering to be below, and this of course couldn't happen. And so this is how you show that L omega 1 charge linear is a model of KP omega. Yeah, so, okay, there's some details to this, but basically this is the idea. So basically, using as a failure of collection and L omega 1 charge linear, you cook up the sigma 1 definition of as a set of all recursive reorderings. Okay, and so of course, so set of all recursive reorderings is well known to be pi11 complete, and thus it couldn't have a sigma 1 definition. Yeah, so this is the contradiction. Okay, so so now let's talk about transitive models of KPU. It's a bit richer world. So we fix some model M. So and then we consider the transitive sets such that they contain the whole domain of our model M as your elements. And so, and of course, and also we require that there are no other your elements. And this will give us this notion transitive model over a given first order model. So transitive. So if this transitive model actually satisfies some KPU, or if the case of empty structure KP, then we call this transitive model an admissible set. Yeah, so it's just standard terminology. And so basically, as in the case of KP, so HF of M is the least admissible set over M. So the more interesting situation is when we actually consider so because of course this so this HF of M is just as discussed this setting for the smallest finite computation or over a given structure. But actually there's some interesting stuff happening if we consider rather than consider HF of M, consider this transitive models where the whole the set of all your elements is a set. Okay, so basically, okay, so yeah, so yeah, so I mean, so the external set of all your elements is an internal set. So basically, this is the model of the theory QPU plus, where QPU plus stands for QPU plus there exists a set such that all your elements are elements of the set. Yeah, so this is called admissible sets above M. And and the least admissible set above M is denoted as a heap of M. So heap here states for hyperarithmetic. So so there will be actually the explanation why this it's called heap. So and how it's connected to hyperarithmetic sets. So yeah. Yeah. So basically, so let's discuss what actually a heap of M is. So we consider this constructible models of KPU. So basically, the constructible sets over a given model M are defined by straightforward transfinite recursion. Yeah, so basically it's more or less the same thing as the usual definition of constructible universe. However, relativized to a model M. So we start with empty set. We start with model M, and on successor stage we take union of M and all definable subsets of the previous level. And of course, when we're talking about definable sets, we treat this L alpha plus 1 of M as this structure in this kind of signature. So we have this predicates from the initial model and membership predicate. And thus, so naturally, we built up this this level of continuous as this transitive models that contain M as an element. Okay, at least start from L1. So in L0, do not do it, but okay, it's a special case. Okay, so let for admissible set A, let O A be this order type of ordinals in this admissible set. So or basically suprema of all ordinals that are elements of the set. Okay, so now actually constructible. So it's possible to formalize the theory of constructible sets inside Kripke-Platek set theory, and this gives us this list. Basically this list. So basically, if you start with some model of Kripke-Platek set theory, then you could have this constructible universe inside it. So in the constructible universe inside so the transitive model of KPU is simply this L alpha, where alpha is this ordinal of this admissible set. So basically, restriction of constructible universe up to the level of this height of your admissible set. And so in fact, it's possible to show in KPU that this constructible internal constructible universe always satisfies action of Kripke-Platek set theorem. And this is basically and that's this is kind of a list. As in the case of ZFC, so constructible universe is the least internal model, and so from experimental point of view, this gives us this theorem. Yeah. Yeah, so okay. Yeah, and so from from this, of course, it follows that if you consider, say, a least ordinal such that it's the height of some admissible set, and then you consider a constructible universe up to this level, this will give you the least transitive model over Gödel model M. So because this level of constructible universe will be containing arbitrarily transitive model of KPU plus over your model M. Yeah. So thus, so this definition of heap of M will be also correct. Oh, but in fact, okay. But of course, so what we talked about. So before, so it was there was no explanation why exactly Kripke-Platek theory. So why wouldn't we want to take some stronger theory? So because in fact, so this basic development of that theory would work in a stronger theory as well. This facts about constructible models actually would work so in reasonable stronger theories as well. So yeah, so this no much explanation why exactly Kripke-Platek theory. But here we came to the fact where actually the fact that Kripke-Platek theory is weak starting to play a role. Okay. Okay, now consider ill-founded models of KPU. So basically now instead of having this set theoretic part to be some just standard set with standard membership etiquette, we consider these models KPU just as usual first order structures. And thus, of course, they are not standard models where membership predicate is not necessarily well found. However, of course, for any given model, we could consider a well-founded part of this model. That is the set of all elements from which there are no infinite descending chain. Okay. And now the theorem is that actually for models for ill-founded models KPU, the well-founded part of the model is always a model of KPU. Oh, okay, KPU plus. Yeah. And in fact, so of course, then using standard Mostovsky collapse. So well-founded part always should be the more transitive model, but it's boring part. But but interesting. What interesting is that happens here is that so this well-founded part is always a model of KPU. Plus, of course, non-trivial. So the trivial axiom to check is axiom of sigma 1 collection. All the other axioms are more or less trivial. So this basic axiom that more okay, it's more or less straightforward to show that they hold. So axiom of foundation holds automatically in all well-founded models. So it's non-issue as well. So there is some special thing about axiom of sigma 1 collection. Yeah. Yeah, so basically this is proved like the following. So you consider some model of some ill-founded model of Kripke-Platek set theorem. So then, and you want to show that collection holds in well-founded parts. So you consider some set from the well-founded parts and assume for contradictions that collection fails. So there is a sigma 1 function that kind of its range. It's good. What should happen is that so what are actually ill-founded models? So ill-founded models are the models where the basically in Kripke-Platek you could define the notion of a rank of the set as so if a model is ill-founded, it means that so basically you have something like this. So you start with some ordinals, and then at some point standard ordinals stop, and you have this ill-founded part of non-standard ordinals. And so well-founded part of course consists of the set such that the rank is a standard set. Is a standard order. So now basically, if you have this sigma non-collectible sigma function, basically it will mean that you will have this sigma one function. So basically, the function, the corresponding functions on ranks will be unbounded in well-founded part. However, if you would have such an unbounded function in well-founded part, in fact, this would mean so then we would be able to apply collection to it in this ill-founded model, and this would give us this bound for this unbounded function in this function that was unbounded in well-founded part, and this will give us this suprema of all the ordinals. And hence, this suprema should also be in well-founded part, because basically it's suprema of ordinals in well-founded part. It couldn't really happen to be in ill-founded part, but here's a contradiction, because we assume that this function was unbounded in well-founded part, but it's actually bounded. Yeah, so basically it's a very easy proof, but it's very nice. I think it's very nice. It really is special for the case of sigma one collection. For other axioms. Okay. Yeah, and so from this, of course, it follows that heap M is so it's actually initial segment of arbitrary model of QPU above a given model M. So even if the model is ill-founded, still it's so its initial part is this model is a model to heap of M. Okay. So now let's go to some connection to second order definability. Yeah. So recall that so that's the class of pi11 formulas in a given first order signature is a class of all formulas that start with some universal quantifiers over relations, and then we have a first order formula with these additional relations. Yeah. So basically, it's this. So basically, we allow this quantifiers over predicate symbols. Yeah, universal quantifiers over predicate symbols. So it's actually quite common to rather give monadic version of second order language where instead of quantifiers over predicates of arbitrarities, you have quantifiers over unary predicates. However, so also it's the same for say expressive enough structures for namely if a structure supports a pairing function, it would be the same. However, in general, these are two distinct notions. Yeah, and so the notion, this notion actually have a better correspondence with the theory of the theory of admissible sets. Yeah. And so now actually the theory is that sigma one definability in heap of M is the same as pi1 definability in M, at least for countable models M. Yeah, and so one part of the implication is called for countable models as well. So basically, if so sigma one sets in heap are pi1 definable. It's always holds, but the other direction holds only for countable models. Okay, so how? Okay, so now actually, and so from this it's quite easy to show that the corollary that actually justifies the name heap. So namely, as a set is delta 1 definable, so pi1 definable, and such as so the set is delta 1 definable if it is pi1 definable and its complement is pi1 definable. And now the corollary is that as a set is delta 1 definable if and only if it's an element of heap. Yeah, so this is, and basically, and of course, in the case if as M you would take the standard model of arithmetic, so delta 1 definable sets in standard model arithmetic is other sets not just hyperarithmetical sets, and of course this and also if you consider heap over standard model arithmetic, the subset of nationals in this heap of N would be exactly hyperarithmetical sets. Okay, yeah, and so basically, of course, very easy to prove from this theorem. So, namely, of course, if if set is delta 1 definable, so basically, then we will have the sigma 1 definition for it and its complement, and when we have sigma 1 definition for the set and its complement, then basically it's easy to construct. Yeah, then we could make the separate. So that means that it's delta 1 in the term of KPU, and actually KPU proves axiom of delta 1 separation. So basically, it's easy corollary from delta 0 separation and sigma 1 collection. Yeah, and so and as direction is very easy. So of course, this set is element of heap. Then it's at the same time a sigma 1 definable, and its complement is sigma 1 definable because hit and complement even delta 0 definable. So it's, and of course it will be delta 1 so then it will be pi1 definable and its complement pi1 definable. Okay, so this was for corollary, and so now for theorem. So of course it's a bit more complicated to prove. Okay, yeah. So we have actually before we have prepared machinery just for one part of this theorem. So if set is sigma 1 in heap, so let's show that it's pi1 definable in M. Basically, the point here is that we could use this corollary about arbitrary models KPU plus. So the idea would be that actually using pi1, so this so in pi1 formulas actually we could quantify over all the countable over all models of so all models for KPU plus over model M, as long as this model have the same cardinality as M. So we could say that something holds for all models KPU plus over model M. And since, in fact, so all models KPU plus contain heap of M as an initial segment, something is so if some sigma 1 formula holds in heap of M, it actually holds in all models of KPU plus above M. And thus, in fact, and so in particular, of course, it holds in heap M itself. And so basically, this means that so sigma formula heap it holds in heap of M if and only if it holds in all models KPU plus above M. And the latter could be expressed by pi1. So this was for first one direction. Other direction is a bit more complicated, and basically the idea was to show the the point is that the truth of pi11 sentences. So the pi11 sentence is true if and only if it's provable in omega logic. Sorry, not in omega logic, in M logic, where M logic is the generalization of omega logic to the case of the model M. And now the point is that inside heap of M, we have the theory of proofs in M logic, and so since there is this what's known as bar-wise completeness theorem, but basically it allows you to establish. So basically, there is the completeness of omega proofs. This is sorry, not omega. The completeness of proofs in M logic that live inside this model heap of M. But here actually this computability of M plays a role because this is a bar-wise completeness theorem works only for countable models. Yeah, and this is basically how you prove that direction. So basically, this sigma formula states that there exists this proof in M logic of your pi11 sentence. Okay. Okay. So now to a different interesting application of this heap of M. So recall that a model recursively saturated if so if it's saturated for computable types, so namely if you have some namely for any computable set of formulas depending on the fixed set of variable x, if there is a witness for conjunction of any finite subset of phi, then there is this in our model there should be a witness for the whole set phi. Yeah, so this is what's called recursive saturation. And in fact, so there is this classical result by Barweis and Schlipp. I think it's a very nice one. So namely, they show that M is recursively saturated if and only if heap of M. So if and only if ordinals in heap of M are boring. So that means so of course in any all heap of M always will contain the standard okay, so actually I think right. Okay, so basically a heap of M always will contain all natural numbers. It's it couldn't happen otherwise. However, in general, of course, so before we seen only the case of the essentially standard point of natural numbers, or which more or less the same as the case of theory KP, where this is kind of smallest model that contain all naturals, so the set of all naturals were in fact L omega-1 Church-Kleene. However, in general, there are models where it's not this, so there are models where heap of M have a small amount of ordinals. So it's just omega. And those models are precisely recursively saturated models. Yeah, and so of course the notion of recursively saturated model it's a rather important one. Namely, so in the case of in the case of countable models, so the model is recursively saturated if and only it's resplendent, and so this basically means so that that sigma on one sentence holds in the model if and only if there is elementary extension where this sigma on one sentence holds. So it's a very useful tool if one wants to do some model theoretic extension. At least I think in the case of models of arithmetic, something like this. Yeah. Okay. Yeah. Okay, yeah, so I think I will give the proof of this. And finally, so I think so. What I think this so talking about this application of the theory KP. So actually, there was quite a lot of application of Kripke-Platek theory to prove theory. Namely, so this, if you know, so in proof theory there's major program of ordinal analysis, so where people try to calculate proof theoretic ordinals of various strong theories. So namely, this primary focus in on the subsystem of second-order arithmetic, because so if you look at say X subsystem second-order arithmetic, something like AC0, that is more or less the same as PA. So it was the proof theoretic ordinal of PA was known for quite a long time. So it essentially was calculated by Gerhard Janssen. However, so this question of what is the proof theoretic ordinal of the full second-order arithmetic is still open. So it's so this program, so where people essentially try to look at the series in this interval between so something weak, something like AC0 to up to this a full second-order arithmetic. And so when we go to relatively strong fragments, so and relatively strong here means something like, so basically fragments that are something like pi11 comprehension and strong. So if people familiar with reverse mathematics, so pi11 comprehension is this series that sits on the top of Simpson's big five. And yeah. And so, yeah, so of course, and so what happening there is that for the stronger systems of second-order arithmetic, in fact, it's rather so it's happened to be rather useful to, rather than considering the system second-order arithmetic themselves, to consider various extensions of Kripke-Platek set theory that corresponds to the systems of second-order arithmetic. So okay, so if you're talking about this connections of Kripke-Platek set theory to proof theory, first the Kripke theory, of course, theory KP is more without infinity is more or less the same as piano arithmetic. So because it's if you don't have axiom of infinity, so you couldn't prove existence of infinite set, and thus say if you look at say what really the theory could prove, it's not that much. It's basically the same as piano arithmetic. However, if you add axiom of infinity, so you already get much stronger theory. So it's it corresponds to what known as theory of positive inductive definitions. And so this is was really very important here. So basically, this theory of positive inductive definitions kind of this important step in this proof theoretic investigation, because it exhibits first theory exhibiting this what's called predictive properties, and so it's, yeah. And so this, and essentially the other look at theory KP omega is that it's more or less the same as the theory of one-time iterated positive inductive definitions. Yeah. Okay. Okay, but basically, so then if you go beyond this, so what's happening is that basically, so some extension of KP omega corresponds to some so strong fragments of second order arithmetic. So namely, if you consider theory KPI, so it's KP omega plus every set is containing transitive models of Kripke-Platek set theory. Then it will have the same second order consequences as delta 1 to comprehension plus by induction. Yeah, and finally this KP. So this, and then so if you add to KP omega principles of separations, then you will get this so comprehension second order arithmetic, but just one level above. So if you have sigma 1 separation, then you get pi 1 2 comprehension. If you add if you add sigma n comprehension, that then will then you will get pi 1n comprehension in second order arithmetic. Okay, sorry, pi 1n plus 1 comprehension in second order arithmetic. Yeah, and so this is very much in fact this is all very much connected to the theory of so-called large admissible ordinals. So basically, the idea was that so this that Kripke-Platek set theory is kind of this computable analog of Zermelo-Frankel set theory. And in Zermelo-Frankel set theory, we have some we have large cardinal notions, and the point is that this sum of the large cardinal notions typically it's for people familiar, it's small large cardinal, so it's not something like measurable, but something like weakly compact or inaccessible or mal or something like this. So basically, this kind of small large cardinal notions do have their recursive counterparts. So basically, you could have this kind of notions that are much, of course, they are really not cardinal notions, but rather ordinal notions. But they have this similar largeness property. And this is actually, again, so this is a very natural extension of Kripke-Platek set series that have the natural analog in this setting of second order arithmetic. Okay, I think it's more or less all I wanted to talk about.